Hey there, welcome back to 2241. This is our examples 3 video, and here we're going to start working on limits and continuity for multivariable functions. All right, so jumping right in, show that limit of this function right here does not exist. Okay, so when we show that a limit does not exist, typically the idea is that we want to come in from different paths by setting x or y equal to something, or asserting some relationship between them. We want to do our parameterization so that we get different values coming into the same point along those different paths. And so here are some easy choices. If we just set x equal to 0, we get the path along the y-axis. Maybe write that down actually. So this is a path along the y-axis. And our limit then looks like the limit as y goes to 0 of, okay, if x is 0, that goes away and that goes away, and we just have y squared over y squared, minus in front, and so we get -1 because these two cancel out. And again, they cancel out because y is not equal to 0, it's approaching 0. Okay, so that's our limit approaching along the y-axis. What happens along the x-axis when x equals 0, or when y equals 0? Now, we get the limit as x goes to 0, but these two terms cancel out. And this time, we don't have that minus in front. So these two terms cancel, and we get +1. And the issue is that these two things are not equal, and therefore the limit does not exist. Okay. Another thing that we could have done is we could have set y equal to x, and then we would get limit as x goes to 0 or y goes to 0, whichever, of x squared minus x squared over 2x squared. And this is 0. So we get another value that's not equal to the other two. So multivariable limits can have a little bit more nuance to them than single variable limits. All right, so let's look at the next one. We're given a function this time and told to figure out whether the limit at 0, 0 of f of xy exists. Okay, so let's check. We set x equal to 0 and y equal to 0, we get f of 0, y equals, well, wait, x is on top here times a bunch of stuff, so this is just 0. And f of x 0 also equals 0. Okay, so limit along these paths, we'll call them P and Q, maybe P1 and P2. Those paths. So limit along P1, P2 of f is 0. Okay, but does that mean that the limit as x approaches 0 in general of f exists? Well, no, it doesn't, because we only chose 2 paths, and there are infinitely many paths that we can come in to 0, 0 along. So here's where that last path option that we did above will come in handy. So P3 is going to be y equals x, and now we have f of x comma x. Let's see what happens there. It's awful today. X comma x gives us x squared in the numerator and 2x squared in the denominator. Now we get that cancellation that we had before, and this function ends up being just equal to 1/2 everywhere except 0. And so the limit along P3 of f equals not 1/2. And these two things are not equal, so the limit does not exist. Okay. So that's pretty much how those ones go. Let's look at this next one and see what happens. So here, we're given a slightly different function. And we want to see, well, what happens when I try those paths that I looked at a second ago. Well, if I try, I can see that if I try x equals 0, y equals 0, then I get the same thing, g of 0x equal g of 0y. 0y, g of x 0 equals 0. Okay. And if I try y equals x, let's see what happens, because that worked last time. So g of x comma x equals, that'll be x cubed on top over x squared plus x to the 4th. Okay, that's a little more interesting. Now if I divide by x to the 4th power on top and bottom, I get, sorry, not x to the 4th, x to the 3rd. I get 1 over x on the bottom plus x. Okay, and now limit as x goes to 0 of g of x is infinity, I think. Yeah, so this goes to 0, and this also goes to 0, but now I have 1 over 0 plus 0, and that is, oh, no, I'm sorry. That's not correct. And now I have limit as x goes to 0 of g of x. And now I want to divide by x one more time. So 1 over x over. And now if I let x go to 0, then this term becomes infinite, this term becomes 0, and so I have 1 over infinite, and this becomes 0. Okay. If you wanted to, you could use L'Hopital's rule too. And that would give you, what, 3x squared over 2x plus 4x cubed, and then do it again, and you get 6x over 2 plus 12 x squared, and finally 6 over 4x, and this limits to 0. So that also gives you 0. Okay, so we came in along 3 different paths and got 0. Does that mean that our limit is 0? Not so much. So, oh, actually, I don't want to erase all that, sorry. I want to do a little bit more work here. Let's try a different path. And so what if we use the path instead, x equal y squared? And if we look at our function over here, we might see a little bit better why that might be a good guess. So I have y squared here and y to the 4th down here. If I set x equal to y squared, then I get y to the 4th up here and y squared squared right there. So that then gives me the same sort of thing that I saw above. And so what does g of y squared y look like? Y to the 4th power over 2y to the fourth power, and I get that cancellation that I wanted again, and now I see that if I come in along this path, I have 1/2 as g. And so limit as y goes to 0 of g of y squared y equals 1/2, which is not equal to any of our previous limits. So the limit does not exist. Okay, so there are lots and lots of different ways for limits to fail to exist. Move this up a little bit. Now, let's look at this limit. H of xy equals 3x squared y over x squared plus y squared. And I want to compute this limit if it exists. Okay. I claim that this limit does exist. Let's check our standard parameterizations here. X equals 0, y equals 0, just as evidence, and then let's do something a little more interesting with this one. Let's say we do y equal m times x for our parameterizations. And so we have h of 0y is 0. H of x0 is also 0. And h of x mx, what does this one look like? 3x squared mx over x squared plus m squared x squared. All right, simplify that a little bit. We have 3mx cubed over 1 plus m squared x squared. Okay, and so this is an x cubed over an x squared thing, and that becomes just a linear function. Sorry, my m's don't look great there. But with this coefficient in front, and these are just constants. M is any number from 0 up to infinity, negative infinity to infinity. And if I take the limit as x goes to 0 here, then this gives me 0. Okay, so that works as well. What about our quadratic parameterization? So let's try y equal alpha x squared, something like that. And so now we have h of x alpha x squared. That is going to give me 3 alpha x to the fourth over x squared plus alpha squared x to the fourth. Okay. And now, again, I see that this is well, I have a little bit of cancellation here. Cancel out an x squared from everything. And then I'll get 3 alpha x squared over 1 plus alpha squared x squared. And that is easier to look at if I divide the top and bottom by x squared. So I have 1 over x squared plus alpha squared. Okay, and then limit as x goes to 0 of this is okay, so limit as x goes to 0 of this. This is infinity, and so we have 3 over 3 alpha over infinity plus alpha squared. Well, that's 0. Okay, because alpha is just some finite number. Okay, so we're getting 0 over and over and over again over all these parameterizations, and I think this limit exists. So how do I show it? Well, you can do the epsilon delta thing. That's difficult, and it's probably not what you need in this class. So instead, we'll do this. We'll use polar coordinates. And this is how you handle showing that limits exist for these types of problems. And polar coordinates, if you don't remember, are just the parameterizations you get from the unit circle. So x equals r cosine theta. I guess not unit circle in this case because we have a radius. But x equals r cosine theta and y equals r sine theta. And so now my two parameters are r and theta, and I have a different way of specifying points in the plane. Okay, so if I substitute these in, I also have that x squared plus y squared equals r squared. That's sometimes useful. And the other one is that theta equals tangent of theta equals y over x. So now I have some equations that allow me to go back and forth between r and x, or x and y, and r and theta. And if I plug these into my function h, so I have h of x, y, and I want this to be h of x, which now depends on r and theta, and y, which now depends on r and theta. Well, we have 3x squared, which is r cosine of theta squared, times y, r sine of theta, divided by r cosine of theta squared plus r sine of theta to the fourth power. Now what? Okay. Well, I've got r, I can factor out all these r's. I've got 3r cubed sine theta cosine squared theta over, all right, and I have an r squared that I can factor out of everything, cosine squared plus r squared sine squared theta, sine to the fourth. All right, and now I want to look at the limit as r goes to 0. So, all right, do some cancellation here. And we'll look at, let's rewrite this. Okay, so we have, let's look at our r parts here. 3r sine theta cosine squared theta. And I know this looks complicated, bear with me. Plus r squared sine to the fourth theta. Okay, now we'll do our division trick. Come over here to do that. We have 3 sine theta cosine squared theta divided by cosine of theta over r plus r cosine squared r sine to the fourth power theta. All right, and now I want to think about what happens as r goes to 0. Well, as r goes to 0, this term right here goes to 0. Because it's for any value of theta, sine is a finite number. And if I multiply that by 0, I get 0. Okay, so that term goes away in the limit. And right here, well, now, again, cosine is a finite number for any value of theta. But if I divide by a very, very small number, this becomes very, very large. So this term tends to infinity. Thus, I have, for any theta, 3 sine of theta cosine squared of theta over infinity. And no matter what finite value I put up here, this forces the limit to be 0. Okay, so we have shown that if you come in along any path, then the limit ends up being 0. Okay, so the limit in general as x, y approaches 0, 0 of h of x, y exists and is equal to 0. So that is how you compute limits that do exist. Note that we did have to use a little bit of the standard parameterization stuff to kind of get the idea that the limit might exist, because nothing is working to show that it doesn't. And then this is your trick to show that something does exist. All right, we have a few more problems here. Let's just get through them. So it says compute the limit as xy goes to 1, 2 of f for this function. And it says use continuity. Okay, well, this is essentially the idea that we just evaluate at 1, 2. Why does this work? Okay, because f is a continuous function. So note f is a polynomial. So f is continuous everywhere. There's no values of x and y I can plug in to get 1 over 0 or the square root or log issues. So f is just continuous everywhere. All right, so that means that limit of f of x, y is equal to f of limit of x, y. Okay, and that just means that this is f of 1, 2. Okay, so I can just compute f of 1, 2, which is 1 squared, 2 cubed, minus 1 cubed, 2 squared, plus 3 times 1 plus 2 times 2. All right, so 8 minus 4 plus 3 plus 4. And we get 11. And that's it. That's our limit. So when functions are continuous, it's very, very easy to compute limits. You just evaluate. Continuity is literally the property that you need for a function to avoid having to do all of those weird limit tricks. All right, so now let's find the domain of continuity of f of xy equals this thing. Where is this function continuous? Where is f discontinuous? So where are the issues? Okay, so we don't see any square roots, we don't see any logs, but we do see division. And so we want to be careful right here. So x squared plus y squared equals 0. If that happens, then I have a problem. Okay. Now, x squared and y squared are positive numbers. They're being added, or non-negative numbers. They're being added together. So the only way I can get 0 out is if both x and y are 0. All right, so that's the only point that I have trouble at. And that means that the domain of continuity of f is, actually, I usually write this as CONT f. Let's do it this way. CTS of f. Continuous f is equal to the set of all x, y in R2, so that x is not equal to 0 or y, or y is not equal to 0. Another way to put this is that I don't want this. So R2 minus this 1 point. That's the entire domain of my function where it's continuous. It's also the domain of my function, but that's the idea there. So for any points of discontinuity, can f of AB be defined to make f continuous everywhere? Okay, so can I just choose f of 0, 0 to be equal to something so that f is continuous? Okay, well, now I need to know what the limit as x goes, or as xy goes to 0, 0 of f of xy is. Okay. So if there is a limit, then I can define f to be that value, and that will make things continuous because I just forced the value to be exactly what it should be. Well, we looked at this problem on the previous page, right here, and we saw, I get -1, 1, or 0, depending on how I approach the limit here. And so this limit does not exist. This does not exist, which means no, there is no suitable choice for f of 0, 0. So this function cannot be made continuous everywhere. All right, a few more. Where is this function continuous? All right, same as before. We look for 1 over 0, square root of a negative number, or log of a non-positive. And so the only issue we have here is 1 over 0. That is when x equals 0. But we know that this is the whole y-axis. Okay, so this function has problems along the entire y-axis. And so the domain of continuity for h is everything except x equal 0. Okay, that's all pairs xy where x is not equal to 0. Okay, and that's it. All we're being asked to do here is find the domain of continuity. All right, so let's look at our last problem here. So let f of xy equals 0 if y is less equal 0 and y or y greater or equal to x to the fourth, and f of xy equal 1 if otherwise. F of xy equal 1 in the other case, if we're between 0 and x to the fourth. All right, so what do we want to do? We want to show that the limit as xy goes to 0 is equal to 0 along any path of this form, m times x to the a, where a is less than or equal to, or less than 4. And then we'll also find out that despite that, f is still discontinuous at 0. In fact, it's discontinuous along both of these curves. All right, so let's draw our domain here, actually. X, y, and what does the curve y equal x squared, or x to the fourth, look like? Well, it's kind of a steep parabola, sort of like this. A very, very steep parabola. I'm sure that this is actually a parabola based on how the computer computes it, but that's fine. So I'll just pretend that that's x to the fourth. And now we'll figure out how to do this problem. So it says along any path of this form. Essentially, they're giving us the path to check. So f of x comma m x to the fourth, or not fourth, a power. And well, I don't know exactly what that looks like. Essentially, we have something that looks like maybe a cubic curve, And if you zoom in on the cubic graph on the x-axis here, and we say, all right, maybe here's 1. The square graph looks something like that. And then the cubic graph is going to be a little bit steeper. Maybe a little more like that. And then the quartic graph should be even steeper than that. And so what we want is to figure out, okay, for y equal mx to the a power, where does this intersect y equal x to the 4th power? So what is that intersection? All right. Well, let's check. If I want to find the intersection point between two curves, I set them equal to each other, correct? All right. So we have mx to the a equals x to the 4th. All right, so this is now a polynomial equation. Okay, maybe pseudo-polynomial, because a can be a real number. We'll say this is equal to 0. And we know that a is less than 4. So 4 minus a is greater than 0. And that means we can factor out x to the a from both parts here. So we get x to the 4 minus a minus m equals 0. And now that tells us that okay, either x to the a equals 0 or x to the 4 minus a equals m. All right, so this one is the stupid case. That's this solution down here. And we want to know what the other intersection point is. So x equals m to the 1 over 4 minus a power. And so that's what happens if we take this cubic curve here in the middle and scale it down a little bit. So this intersection point will move, and we want to know, okay, what does this function look like in between there? Okay, so there's our intersection point. M to the 1 over 4 minus a. Actually, there should be a point, so that is the x-coordinate, and the y-coordinate is that to the 4th power, so m to the 4 over 4 minus a. So there's our intersection. Technically, you also have the 0.00 in there. As well. But this is the point that we care about. All right, so now what I want to do is know what happens to this curve in between x equals 0 and x equals m to the 1 over 4 minus a. So I'm looking at something right here, maybe, and I want to know, okay, is x cubed or x to the 4th greater there in between? So what's a number? We need a number between 0 and m to the 1 over 4 minus a power. Well, okay, the easiest is probably just to take this number and divide it by 2. So let's say m to the 1 over 4 minus a power, divide by 2. And now I want to know, all right, is that bigger if I do m times that number to the a power? Or is it bigger if I just take it to the 4th power? So do I put a less than, greater than, or equal to here? I don't know yet. So we have to check. All right, so let's just put an equal sign there for now. Or, maybe we can put like a little tilde there. Pretend it's like an equal sign. So we don't know yet. Then we have m times m to the a over 4 minus a over 2, and 2 to the a power. That's somehow related to m to the 4 over 4 minus a over 2 to the 4 power. All right, so let's simplify this a little bit more. If I add these two together, I have m to the 1 plus a over 4 minus a. And so now I want to work on that expression in the exponent. So 1 plus a over 4 minus a. If I add these together, I get 4 minus a plus a over 4 minus a. This is equal to 4 over 4 minus a. All right, so we have m to the 4 over 4 minus a over 2 to the a here. This is somehow related to m to the 4 over 4 minus a over 2 to the 4. And, well, these two in the numerator are exactly the same. So really the only deciding factor here is 2 to the a versus 2 to the 4th power. Okay, well, I know that a was chosen to be less than 4, and that means that 2 to the a is going to be less than 2 to the 4. And I guess it's probably a good idea to put in a is greater than 0 as well. Okay, and if 2 to the a is less than 2 to the 4, well, I can flip them. Cross divide maybe is an easier way to think of that. And that gives me that 1 over 2 to the 4 is less than 1 over 2 to the a. All right, well, now I just have to think, all right, I cancel out the m here, and I have exactly this equation, or this inequality. So this should be a greater than symbol. And that tells me that m x to the a is greater than x to the 4th for x between 0 and m to the 1 over 4 minus a power. Okay, why did I need to do all this? Okay, let's go back and remember, I was looking at this function that was defined in different ways. So over here, it's 1 between these two curves, and out here, it's 0 on the other side. So the function is, make that straight line. There we go. Okay, so the function is that gives you back 1 in these two regions and 0 over here. And so I need to know, how is this path y equal mx to the a approaching 0? Is it doing something like this? Or is it doing something like this? Or is it doing something like it crosses a few times and then stays in one? Or is it crossing back and forth over and over again? Okay, and so what we just did is we showed, well, no, it actually just crosses once and then stays above until it hits 0, where it crosses again. And that tells us that in this entire region of the path, which is the end of the path, so at the beginning it might be 1, but at the end, f is equal to 0. So when I look at limit as x tends to 0 of f of x comma m x to the a less than 4, this is equal to limit as x goes to 0 of 0. And that's 0. Okay, but then this function is discontinuous. So we've shown that this path gives us a limit of 0, and that this whole class of paths gives us limits of 0. But if I look at limit as x goes to 0 of f of x, x to the 5th, let's try that, f of x, x to the 5th, well, x to the 4th is going to be greater than x to the 5th for x between 0 and 1. And so now this path gets in between the x-axis and the curve x to the 4th. So now the limit as x goes to 0 of f of x to the 4th, sorry, x to the 4th, x to the 5th is equal to 1, implies that the limit does not exist.